Okay, for example number 7, we need to first look at two definitions here. The first definition is the complex conjugate theorem. According to the linear factorization theorem, a polynomial function will have the same number of factors as its degree, and each factor will be in the form x minus c, where c is a complex number. If the polynomial function f has real coefficients and a complex zero in the form a plus bi, then the complex conjugate of the zero a minus bi is also a zero. The other definition that we need to make sure that we're familiar with is the fundamental theorem of algebra. The fundamental theorem of algebra states that if f of x is a polynomial degree of n greater than 0, then f of x has at least one complex zero. We can use this theorem to argue that if f of x is a polynomial of degree n is greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors. So the form is written as f of x, which is equal to a times x minus c1, x minus c2, all the way to x minus cn, where c1, c2, and cn are complex numbers. Therefore, f of x has n roots if we allow for multiplicities. So how do we go about this? Well, given the zeros of the polynomial function f and a point c and f of c on the graph of the function, we're going to use the linear factorization theorem to find the polynomial function. Step 1, we're going to use the zeros to construct the linear factors of the polynomial. Step 2, we're going to multiply the linear factors to expand the polynomial. Step 3, we're going to substitute the ordered pair into the function to determine the leading coefficient, and then we're going to simplify. So for example 7, we want to find a fourth degree polynomial with real coefficients that has the zeros of -3 to I, such that we have an ordered pair that when x is -2, the output y is 100. Now, because x is equal to I is a 0, by the complex conjugate theorem, x equals -I is also a 0. The polynomial must have factors of x plus 3, x minus 2, x minus I, and x plus I. Since we are looking for a degree 4 polynomial and now have 4 zeros, we have all 4 factors. So let's begin by multiplying these factors. So we have our form where it's f of x is equal to a times x plus 3 times x minus 1 times x minus I times x plus I. Now we're going to multiply x plus 3 times x minus 2. When we multiply them together, we should get x squared plus x minus 6. And then when we multiply x minus I times x plus I, then that becomes x squared plus 1. And that's how we get that second step. And then we need to multiply x plus 2 times x squared plus x minus 6. So what we can do is we can go ahead and then multiply it with the box method. So we have x squared plus 1, and then we have x squared, x, and then minus 6. So we have 2 rows and 3 columns. X squared times x squared is x to the 4th. X squared times x is x cubed. X squared times minus 6 is minus 6x squared. 1 times x squared is x squared. 1 times x is x. And 1 times -6 is -6. And so if we combine like terms, we see that we have x to the 4th. We have x cubed. If we combine -6x squared and x squared, that gives us negative 5x squared. We have x, and then we have minus 6. So that gives us this result. Now, the next thing that we want to do is we need to figure out what the value of a is. So now we have to use this ordered pair that was given. And so what that tells us is we need to find a to ensure that f of negative 2 equals 100. So we're going to substitute x to equal negative 2 and f of 2, meaning the output is 100, into f of x. So now f of x becomes 100, and then the value of x into that polynomial becomes negative 2. So now we need to figure all this out so we can figure out what the value of a is. So when we use order of operations, that gives us a value of negative 20. So a times negative 20 is equal to 100. Now since we want to isolate a, we're going to divide both sides by negative 20. So 100 divided by negative 20 gives you negative 5. So now we know the value of a is negative 5. And now we can plug that back into our function. So now rewriting what we got in this last step, we can substitute a to be negative 5, and then x to the fourth plus x cubed minus 5x squared plus x minus 6. And then if we distribute the negative 5 to each term, then we end up with the polynomial f of x, which is equal to negative 5x to the fourth minus 5x cubed plus 25x squared minus 5x plus 30. Now, we found that both I and negative I were zeros, but only one of these zeros needed to be given. If I is a zero of a polynomial with real coefficients, then negative I must also be a zero of the polynomial, because negative I is the complex conjugate of I. So it's very important to make sure that you make note of that. So here's a Q&A. If 2 plus 3i were given as a zero of a polynomial with real coefficients, would 2 minus 3i also need to be a zero? Well, the answer would be yes, because when any complex number with an imaginary component is given as a zero of a polynomial with real coefficients, the conjugate must also be a zero of the polynomial.